All right. Hello, everyone at CppCon. I'm Ben Sachs. For those of you who don't know me, my company, Sachs & Associates, does professional level training in C and C++ programming for companies all over the world. And I'm here to talk about pointers in memory. There's a fair bit to say, so let's get to it. Oh, before I get started, let me say, feel free to ask questions in the chat or using the Q&A in Remo. I have someone relaying those questions to me, but please understand we're on about a 10 to 15 second delay. So if you type in a question and it doesn't look like I'm responding immediately, I'm not necessarily ignoring you. I might just be receiving it a little bit later on. Okay, with that, let's get started. So C++ has had language support for pointers and arrays all along. It was something that it inherited from C. So from the very earliest days of C++, we could write pointer objects like this or array objects like this. Now, in modern C++, we usually prefer to avoid using these, what I'm going to call raw pointers and arrays, in favor of other more recent developments like smart pointers such as unique pointer or shared pointer, container classes like vector or list, because those types offer a lot of advantages. They have, using the smart pointers and container classes provides a clearer indication of the author's intent, both in terms of the functions you have available and just in terms of the name of the type gives you a clear sense of ownership in the case of smart pointers or the kinds of operations you'll be doing with the type in the case of container classes. And we don't need to worry about releasing resources. So why are we talking about raw pointers and arrays? Well, you might need to use them in some situations. For example, you might have a library that has an interface that's based on raw pointers. This is often the case when we are using a C library, but using it in a C++ project. This also happens when you're accessing hardware at a low level. If you saw Dan Sachs's talk on representing memory mapped objects as devices yesterday, you would have seen some of that. It also happens if you're actually implementing a container class or a smart pointer yourself, because it's very difficult to create a smart pointer with different characteristics from the smart pointers we already have using the smart pointers we already have. And even if none of those things apply, there's a good chance that you just have some older code in your project that will use raw pointers and arrays. So even if you're not programming with them, it's a good idea to be able to understand them. Okay, so here is the basic outline for the talk. I'm going to be starting just with some overview of pointers to objects in general. We will get into array and pointer arithmetic, some related topics like size t and putterdiff t. We will go into pointer type conversions, first involving const and then other types of conversions, and close out with a comparison to references and what you might use pointers for versus what you might use references for. Okay, I suspect that a lot of this is going to be material that's familiar to you, so I'm going to go through it rather quickly, but feel free to stop and ask questions. This is meant to be, if you have, to make sure that we're all on the same page, and just in case I say anything in the details here that's surprising, feel free to jump in and ask. Okay, so a pointer is an object that holds the address of another object, and every pointer has a specific type that it points to. So here we're creating a pointer to an integer or a pointer to an unsigned long, and as we'll see, these objects will only point to integers or unsigned longs, respectively. So when I have an object and I want to get the address of that object, I take its address using the ampersand operator here. So for any object that's of type t, ampersand x, any object x of type t, ampersand x has type pointer to t. So here, when I have an integer and an unsigned long, I want to assign their addresses to the pointers that I created on the last slide. I can do that by assigning ampersand I or ampersand UL to those pointers. In general, you can modify what a pointer points to after it's been created. We'll talk a little bit later about some situations where that doesn't apply. But in many cases, a pointer can be made to point to something else at different times in its life. And this is often what we're using pointers for. We want to be able to operate on the pointer P and expect that sometimes it's pointing to object A here, and sometimes it's pointing to object B here. So I can set up my pointer to point to A initially. At some later point, I can change it to point to B by assigning the address of B to P. I can also have a pointer that doesn't point to anything, that has what we call a null value. And there are a few different ways that we can do this. There's the capital NULL constant. There's 0 counts as a null value. And there's also null putter in lowercase. And null putter is generally the preferred way for reasons I'm about to talk about. But all three of these will work. They're all equivalent in terms of setting P1, P2, and P3 to null values. The reason we generally prefer to use null putter in lowercase is null is a constant that came from C, and it turns out it's actually defined as either 0 or 0 as a long. But either way, it's an integer type. It doesn't actually have a pointer type, even though null was created to be a value for pointers that don't point to anything else. And so this had the surprising effect when we got to C++ and had overloaded functions, that if we had a set of overloaded functions, some of which took integers and some of which took pointers, the caller could call f passing null to that function. And they're probably thinking of null as a pointer constant. The author of this code probably intended to call the f that takes a pointer to a character. But what actually happens is it calls the f that takes an integer, because null is actually a closer match for that version of f. So to prevent that, C++11 added this null putter keyword. Null putter is actually a unique type that has conversions to any pointer type, but it never converts to an integer type. So the result of that is that now we can call f, pass it null putter, and this will convert to any type of pointer that f might take. But it'll never convert to an integer value. So there's no, well, maybe I should say less possibility of confusion in terms of which function might actually be called when I pass a null pointer to it. That's what makes this the preferred way to represent null pointer values in modern C++. All right. When I have a pointer, I can dereference the pointer using the star operator to get to the object that that pointer actually points to. So here I have an integer and an unsigned long. I set up pointers that point to those things. When I access star PI or star PUL, I'm accessing the integer or the unsigned long through those pointers. So this first statement stores a 14 into this pointer, or sorry, into the object that PI points to. This statement adds 2 to whatever value UL points to, or PUL points to. Now, if you're dealing with a null pointer, dereferencing it is something you want to avoid doing. You want to be careful not to dereference a null pointer because the result is undefined behavior. We don't know exactly what bad thing will happen, but it may very well be a bad thing, and we should watch out for that. Okay, A pointer often doesn't have the same lifetime as the object that it points to. So here we have a function f that has a parameter of type pointer to integer. So each time we call f, this parameter starts, a new version of this parameter is created. It starts its lifetime when the function is called, and its lifetime goes throughout the function and ends when we reach the closing curly brace. So here, when I call f, and I pass it the address of an integer I, each pointer only lasts for the duration of a single call to f. But I existed before the call to f, it'll continue to exist after f. It has a completely different lifetime. Done in this direction, there's no real danger here. Where things get a little more complicated is when the pointer outlives the object to which it points. So here's a situation where this function g creates an object, an integer internally into I here. This I is a local value. It will die when we reach the closing curly brace of this function. But g is written to return a pointer to I, which means that when we've returned from g, this pointer that was returned is pointing to something that no longer exists. And so pi is now pointing to a dead object. We call this a dangling pointer. And just like with null pointers, accessing star pi at this point would produce undefined behavior. And we want to watch out for that. That happens because there's not really an object there anymore. There's just the ghost of an object. All right, so moving on to arrays and pointer arithmetic. Arrays in C++ on the surface aren't that much different from the way that they are in other languages. I suppose a lot of languages that we use today are interpreted. So one difference is that when you dimension an array in C++, the dimension of the array, the n here, has to be an integer constant expression, something that can be evaluated at compile time. But otherwise, it behaves a lot like arrays in other languages. The elements are all numbered from 0 to n-1. Oh, no, I wasn't actually referencing life of pi there. I just happened to type in pi as the pointer, and that happens to be pi. So, but no, I didn't really realize that particular pun. Okay, so the elements are numbered 0 through n-1. So the nth element is the first one. It is the first element beyond the end of the array. I can access the 0th element with x square bracket 0. I can access any element, the kth element, but with x square bracket k. Now, I can also access the elements of an array through pointers. I can set up a pointer that points to an element in the array, like this, and then I can modify the value of that element through that pointer. So here I set up a pointer to a character that points to the first element of x. If I write to the character that PC points to, it's the same as if I'd written to x sub 0. And I can adjust that pointer by incrementing it so that it points to other objects in the array as well. If I add 1 to the pointer, that has the effect of moving us to the next element in the array. So now, after this statement, PC points to x sub 1, and assigning to it has the effect of writing a C to x sub 1 rather than x sub 0. So in general, ++p causes p to point to the next array element, and it doesn't matter what the size of the array elements are. So the example I was just showing you used pointers to characters. Characters are always size 1, so ++p in that situation actually would literally add 1 to the underlying value. But if p were a pointer to an integer, then size of int is typically greater than 1. It's often 4 on a lot of modern platforms, in which case ++p would actually have the effect of increasing the underlying value of the pointer by 4, so that it really points to the next integer element in the array. So it's not uncommon to see people use pointers to step through the elements of an array like this. So we start out first time through the loop. This pointer points to the first element, the one with value 1. We increment the pointer each time through the loop so that after that it points to the next element and then the next one after that, so forth. And we stop when we reach the point where the pointer points to the element 1 beyond the end of the array. Oh, yes, someone's asking about the question of using ++p versus p++. For pointers of built-in types like pointer to character and pointer to integer, you won't see much of a difference in performance in almost every case. They have a slightly different meaning. The ++p effectively has a return value. You can assign the value of ++p to something, and what you get is the value of p after doing the increment. If you assign the value of p++ to something, what you get is, what is assigned is the value of p before the increment. That's the key difference, which for some class types that have ++ operators means that ++p is a little bit more efficient than p++. For objects of built-in types, you generally won't notice a difference, but I think it's just a good habit to get into using the prefix ++ for that reason. So this loop goes until we point to the first element after the end of the array, this sort of imaginary phantom element, 1 beyond the end. And we can safely point to this element, or take the address of the equivalent of x sub n in the array, for the purposes of figuring out if we've actually reached the end of the array, or for doing pointer arithmetic involving elements inside the array. But we can't actually read from or write to that element. If we wanted to do one of those things, the result would be undefined behavior. Okay. I can also, in general, adding integers to pointers yields another pointer. So here I have a pointer p. I can get a different pointer q that points k elements later than p in whatever array p points to, and assign that to q by writing p plus k. So here, I say it results in an integer. I'll be more specific about what kind of integer I'm talking about. Right now, I'm just using integer as a generic term. Don't think specifically int or long or something else. Similarly, I can subtract two pointers that point to the same array. So here I have p and q both pointing to the ith and jth elements of array x, respectively. If I subtract p from q here, I get the same result as if I subtracted I from j. It's the difference between the two indices. So here, if I calculate m using the pointers one way, I calculate n using the indices the other way, these two will always be equal. Same result. Now, subtracting two pointers is actually only valid if they both point to elements of the same array, or to that phantom element one beyond the end of the array. If you're subtracting two pointers that point to unrelated objects, the result is undefined behavior. Now, you rarely run into this because almost always you're doing pointer subtraction because you're trying to adjust the position of a pointer in the array. But this is something to be aware of, that it really is only pointers within the same array that can be subtracted. All right. Interestingly, we can also treat the array X as if it were a pointer itself. So I don't actually have to refer to address of X sub 0. I can use X directly and it behaves as if I had written address of X sub 0 for the purposes of initializing a pointer like PI here. And not only can I do that, I can treat object X as if it were a pointer itself and assign to star X, and it has the same result as assigning to the 0th element of X. And in fact, subscripting the square bracket operator, that's actually described as a pointer operation in the standard, not an array operation. So while we typically think of this as being something that we do with arrays, the subscript operator, it's really just a shorthand for this. These two pieces of code are equivalent. Now, you'll generally be understood better. I think using the subscript operator is a clearer way of expressing yourself. But both of these will generate identical code, whether I write it as X sub I or star X plus I. Again, I recommend this one, but you won't actually see a difference in the code. So this raises the question of, is an array really just a pointer? And it's not, but we often get fooled into thinking it is because it behaves so much like a pointer. So here's the distinction. This object X, defined with the square brackets, that's really an array. It's not a pointer type, not the same way that this P here is a pointer type when it's declared with the star operator. So then why does this actually work? Why can I assign directly from X to P, and that has the result of making P point to X's 0th element? The reason that this compiles is because an array, we say an array can decay into a pointer. Decay is a colorful term for what's technically referred to as an array to pointer conversion in the standard. The idea is when the compiler sees this expression, it knows that X is the kind of thing, X is an array type. Arrays are the kind of things that can decay into pointers. So it will treat X as a pointer value for the purpose of doing this assignment. Now, the decay doesn't last very long. It's only momentary, just long enough to do the assignment. X really remains an array, and it's the same as what's going on in this situation here. So if I have a double and an int, two objects, one of type double, one of type int, and I try to add the integer value to the double, this will work. It will compile. What we often say is that this expression converts I to a double. But that's a little bit of an oversimplification because we know that afterwards I is still an integer. What's really happening is something that looks like this, where the compiler creates a temporary object of type double, T here stands for temp, by converting the value of I into a double value. Then it adds the value of that temporary to D, and then it throws away the temporary. So I is always an integer. It's just, but we extract the value of I into an object of type double temporarily to do this assignment. So how can we show that an array really isn't a pointer? Well, for one thing, when we can assign an array to a pointer like this. If I write P equals X, that works just fine. X will decay into a pointer and be suitable for assigning to P. But I can't write this the other way around. I can't assign to an array. I can't assign anything to an array. Doesn't matter whether it's a pointer or something else. Putting an entire array on the left-hand side of an assignment operator just doesn't work. The size of and alignment of operators also produce different results when they're applied to pointers versus arrays. So the size of an array is the size of all the combined total of all of the objects in the array. So size of X here, where X is an array of 32 characters, is 32 times the size of a character, which is 32 because size of char is always defined to be 1. Meanwhile, the size of a pointer to a character is something else. Depending on what platform you're on, it could be 2 bytes, 4 bytes, 8 bytes. 4 or 8 are more likely on most modern machines, but it's not going to be 32 by all likelihood. Similarly, a line of, this gives you the alignment of that a single character is required to have, which is almost certainly 1. But the alignment of a pointer could be 2 or 4 or 8. It's probably the same as the size of the pointer up here. So this is another way that you can tell that arrays aren't really pointer objects. All right, except when they are. Array parameters really are pointers. That is to say, if I write these function declarations, all X is really a pointer in all 3 of these cases, even though it appears to be an array in the later 2. If you look at the size of X, doesn't matter how I write this function, the size of X is always the size of a pointer, not the size of an array. All other arrays that aren't parameters, are really arrays. But in C, they tried to make a simplification they tried to make something more intuitive by allowing you to pass arrays as parameters, and it kind of backfired. So now let's talk about size t and putterdiff t. So there are a number of functions in the standard library that take parameters that represent the size of an object in bytes. So malloc, when I call malloc, I pass it the number of bytes of memory that I want to allocate, and it returns back a pointer to a chunk of memory of that size. In memcopy, I tell it how many bytes to copy from the source to the destination with this third parameter, n. Now, and I'd like to be able to call malloc or memcopy and give it the size of any object I might want. So whatever type n has, however memcopy and malloc are declared, the type of n should be something that can represent the size of any object I might create. And that type exists, and it's called size t. It's defined to be the result of the size of operator. So it's literally size t is defined to be something that can hold any possible result of size of. Now, that might be different sizes on different platforms, because different platforms may have different amounts of memory and therefore have different spaces. Yeah, I will. So to pass an array to a method, you need to compute its size too. Is a question that came up. Yes, I will. Yes, typically what you do to pass, if you really want to pass an array to a function, you pass it as a pointer plus a size, often a size t, but we'll talk about that. We'll get into that in just a bit. But yes, you almost always, when you're intending to pass an array to a function, you need 2 parameters. So Size t might be different sizes on different platforms because different platforms have different sizes of memory and therefore different maximum sizes for objects. But it's always an unsigned type because sizes are never negative. There's no such thing as an object that takes up -3 bytes. It could be long, it might be long, something like that, but the idea is it's supposed to be no larger than it has to be to represent the size of the largest object that the machine exist on that machine. So malloc and memcopy, if you look at their definitions, that parameter has type size t. Now, but you'll notice if you look at other places in the standard library, they also use size t to represent array sizes as well. Size t is the type of value that's returned by strlen, which is really the length of an array. The size of an array is measured in bytes. If I take size of array, that's the size of the array in bytes, which is not necessarily the same thing as the number of elements in the array. If I have an array of integers, it's going to occupy a lot more bytes than it has elements. But the idea here is that the largest possible array is going to be limited by the maximum value of size t. So if we want strlen to be able to return a value that's always going to be within the right range, that is on the same scale as the maximum size in bytes of an array, size t is a good way of representing that. So technically it represents a size in bytes, but it can also be used for other kinds of sizes. Now, what that means, so size t is always an unsigned value. So size t is what that means is that size t is often used as the type of a value to index into an array. As we saw earlier, we can access array elements using either indices or pointers, as I'm showing here. The thing is, though, pointer arithmetic doesn't have to produce a positive value. When I subtract two pointers that both point to the same array, if I subtract p from q, the result is the difference between the index of this 5 and the index of this 2, so 4 and 1. The result is 3. But I can also subtract q from p and get the result -3. Pointer subtraction yields a value of a similar but not quite the same type as size t, called putterdiff t, difference between two pointers. So putterdiff t is designed to be something that can represent any result that you could get by subtracting two pointers that point to the same array. Another way of saying that would be the maximum distance between any two elements in an array in either direction. That should be something that can be represented as putterdiff t. It's always a signed value because the distance can be either positive or negative. Again, like size t, the intent here is that it be no larger than necessary. And it's almost always the equivalent of the signed version of size t. In fact, it's not entirely clear from the standard that it actually can be anything else, although the standard doesn't come right out and say that. So, this has led to an odd result over time, that because putterdiff t is signed and size t is unsigned, but they're both clearly related concepts, it's not uncommon to want to mix them, and you need to be careful about doing that, because when you use putterdiff t and size t together, it's quite possible to get accidental signed to unsigned comparisons. And this is a problem because if you try to compare a signed value to an unsigned value of the same size in C++, the compiler does another one of those temporary conversions. It turns the signed value into an unsigned value and then compares the two unsigned values, which means that if the signed value actually had a negative value in it, the result is that it effectively underflows the negative or the unsigned value, and you get a very large positive integer, which is probably not what you were expecting. So here's an example of a situation where this might come up. I have an array of characters. I'm reading a field from, imagine that I'm parsing a text document that contains fields separated by commas. Here, so I find the next comma, which indicates the end of the field. I subtract field from field end to get the length of that one field, the number of elements in the array. If I compare that length to the size of the buffer, this winds up being an assigned to unsigned comparison, because length is a signed type, putter diff t. Size of returns a size t, which is an unsigned type. It's possible that I could get that kind of underflow there and wind up with code that does something surprising. And one way that this is particularly insidious is that sometimes if you use auto with expressions that could yield size t's or putter diff t's, you want to be careful to keep an eye on which ones are signed and which ones are unsigned, because it's not, where even if you remember that putter diff t here is always signed, it's not immediately obvious in this case that the type deduced for length is signed as well, even though it is also a putter diff t. So that's something to keep an eye on. Now, a lot of compilers will warn you about these types of conversions, but they're just warnings. They're still the kind of thing that can go unheeded, and you want to watch out for that. Okay, the C++ community seems to be moving in the direction of representing sizes with signed values as a way of protecting against this kind of mistake. So in C++20, you will see that there's an S-size function that returns the size of the container as a signed value that can, instead of as an unsigned value. And if you look at C++20 ranges, you'll see that they have methods for getting both the size as both a signed and an unsigned value, depending on which one you want. So we're kind of moving in that direction to avoid this, but it's still something that you need to watch out for. All right, so moving on to type conversions and the meaning of const in pointers. So if I have a basic pointer declaration, p is a pointer to a t, I can add const to it in any of these places, and that will produce some kind of pointer to constant something. Here's what each of them means. Now I'm just going to go through this quickly. For a much deeper discussion of how const affects pointers and references and other types like that, you can see last year's Back to Basics const as a promise talk, and that covers this in a lot more detail. If the const is over here on the left-hand side of the star, it means that p is a pointer to a constant t. I can change which object p points to, but I can't write through p and change the object that p points to. I can make it point to something else, but I can't use it to change the value that it points to. When the const is on the right side of the star, here, this means p is a constant pointer to a t. Now it's the object that is pointed to that remains constant. We can't P will always point to the same object of type T. If we try and assign to it, take the address of some other object and make that the new value that P points to, that won't work. We'll get a compile error. But we can write through the pointer and modify the thing that it points to. Star P is modifiable, P is not. And unsurprisingly, if you have const in both places, you have a const pointer to a constant T, which means you can't change the thing, which object it points to, and you can't use it to change star P either. You can't write through the pointer. You can only read from it. So I've mentioned const here. Anywhere that you can use const, you can actually use volatile as well in general. So you can use const or volatile or both. We collectively refer to them as CV qualifiers. And so I'm going to be talking about const, but the same rules regarding type conversions also apply to volatile. Otherwise, I'm not going to talk very much about volatile. Proper use of that is really outside the scope of this session. Interestingly enough, const expr is not a CV qualifier. Const expr is not always used in places that you could use const. There are places where you can use const expr that you can't use const. There are places that you can use const where you can't use const expr. So we refer, qualification conversions are a kind of safe pointer conversion that adds a CV qualifier to a pointer type. So if I have a pointer to a T, which is qualified by CV qualifiers CV1, I can turn that into a pointer to a CV qualified T with CV2, as long as every qualifier that's in CV1 is in CV2. That is to say, I can add const or volatile, but I can't remove them. So here I have a pointer to a regular plain old T, pointer to a constant T, pointer to a volatile T. I can make PC point to the same object as P, because this is a conversion that adds const. It's perfectly safe to take a pointer to non-const and convert it into a pointer to a const object. I can't go the other direction, though. I can't turn a pointer to a constant object into a pointer to a non-constant object, because that throws away a const. By the same token, I can convert in the direction that adds volatile, but not in the direction that removes volatile. And if I try and convert between the const pointer and the volatile pointer in either direction, neither one of those will work, because in either case, I'm losing either the volatile or the const. I'm adding the other one, but that doesn't change the fact that I'm losing one of them as well. Now, interestingly, const expr, when applied to a pointer, doesn't actually mean the same thing as const in the same place. So these two declarations don't have the same effect. The const expr pointer actually behaves like a const pointer, not a pointer to const. So this is what I mean when I say that const expr is not a CV qualifier. It has different semantics, and as a result, a const expr, an object of a pointer type that is declared const expr, is really more similar to a pointer, to a constant pointer to something, not a pointer to a constant something. All right, moving on to other types of pointer conversions. So accidental pointer conversions were common in early C programs. Over time, programmers discovered that these kinds of conversions between different pointer types could lead to surprising behavior. So even in C, many of the conversions that I'm about to show you are warnings. But but C++ actually treats pointer conversions between pointers of incompatible types as errors. So here I have a pointer to an object of type gadget, a pointer to an object of type widget. I can't take the pointer to a widget and treat it as a pointer to a gadget. I can't take the pointer to a gadget, treat it as an object of type widget. Both of these are errors in C++. Now, I can make the compiler do it anyway by casting, using a reinterpret cast here. But this doesn't actually make it safe. I mean, what I'm effectively doing here is telling the compiler was saying back here, I don't know, looks pretty strange. A pointer to a widget isn't pointing to a gadget. So are you sure you want to do that? Reinterpret cast is your way of saying, yes, I'm sure I want to do that. Let me do it anyway, even though I know that it's strange, that it's a strange thing to do. And if you're careful, that can work. But this can also result in undefined behavior. All we're doing with the cast is making the compiler shut up about this complaint. So a pointer to a derived class object will safely convert to a pointer to a base class object. If I have an object of type derived and I take its address, I can assign the resulting pointer to a pointer to the base class type. I can't go in the other direction. A pointer to base doesn't convert into a pointer to derived, but a pointer to derived will convert into a pointer to base. Otherwise, if I try and access an object through a pointer to some unrelated type, the result is usually undefined behavior. So here, if I have an integer, I take its address and cast that into a pointer to a double, and then I try to write to the double that thing points to, the result that I get is undefined behavior. Because there isn't really a double object there. There's really an int object. Now, some C functions like malloc and free were designed to work with pointers to objects of any type. And so C provided the type void star, pointer to void, as a kind of generic pointer type that could represent a pointer to any kind of object. So that's the return value of malloc, and it's what the free function takes. And a pointer to a void can theoretically point to any kind of object. Now, a C program is happy to convert to or from pointer to void with or without a cast. So that's useful, but it also has this side effect, which means that if I start with a pointer to a gadget, I can assign that to a pointer to void, and then I can assign that pointer to void to a pointer to a widget. And that has the effect of converting a pointer to a gadget into a pointer to a widget without a cast. And this still yields undefined behavior, even though there were no casts involved. C++ tries to protect you against this kind of mistake, only allowing you to convert towards void star, not to convert away from it. In other words, I can take a pointer to a gadget and convert it into a pointer to a void. C++ will let me do this without complaint. If I try and take the pointer to void and assign it to a pointer to a widget, though, this is an error in C++. C won't complain, but C++ will. In C++, I would have to use a cast to force the compiler to accept this, to do this conversion. The idea being that when I convert from a pointer to a T to a pointer to a void, that's a relatively safe thing to do because it turns out you can't actually do very much with a plain old pointer to void. An object of type void doesn't have a size. You can't increment the pointer to make it point to the next void because the compiler doesn't know how big a void is. You can't dereference a pointer to void because objects of type void aren't really a thing. Void is just a placeholder type in that sense. And this is actually true. Void is actually an incomplete type. And so if you have other incomplete types, that is, types that you've declared but not defined, the same thing is also true. You can't write any of these expressions for a pointer to that type either. On the other hand, if I convert a pointer to void into a pointer to some other type of object, here, this is a dangerous thing to do, because now I'm adding information to this pointer. I'm saying you should be able to use this pointer as if it were a pointer to a t. And if it isn't really a pointer to a t, we could get undefined behavior as a result. That's why this direction you need to cast. All right. Do we need any cast to convert from a pointer to constant t to pointer to constant void? If you're converting from pointer to constant t to pointer to constant void, that's this kind of conversion, converting from a pointer to a t into a pointer to a void. You're preserving the const, and the only thing that's changing is t is becoming void. That's a safe conversion. That doesn't require a cast. Going in the other direction, pointer to constant void to pointer to constant t, that requires a reinterpret cast, because that's the same. The danger is the same as converting a pointer to a non-constant void into a pointer to a non-constant t. You can do things with a pointer to a t that you can't do with a pointer to a void. Okay, so references are another way of referring to objects through an alias aside from pointers. So I declare references using the ampersand operator here. And this defines Ri to be a reference to an integer that is referring to object I here. After this point, anytime I use Ri in an expression, it's as if I'd written I there. So it's effectively, you can think of a reference as a kind of a constant pointer. It's effectively a pointer that always points to the same thing and always has a star in front of it whenever you use it later on. So anything that you could write using references, you could also write using constant pointers. Once you create a reference, you can't change to anything else. Change it to anything else. Is it really undefined behavior, or will it treat it as if the memory was laid out for the target type? It's really undefined behavior. You might get away with undefined behavior. Most platforms will try and treat it as if it's a pointer to the target type. The reason it's undefined behavior is because if there isn't actually an object of type t there, then treating something as a t could give you strange results. Are these unsafe casts effectively the same as a union with different members? Yes, often that's the case. Converting, if you assign to one member of a union and then try to access a different member of the union, yes, you'll generally get similar behavior to trying to access an object through a pointer to the wrong type. So once you create a reference, you can't change it to refer to something else, because this statement binds binds the object Ri to I. But any later use of Ri is actually as if I'd written I. So this is not changing what Ri refers to. It's assigning J to the object that Ri refers to, namely I. but you didn't indicate that even a write is unsafe, which is normal with unions. Oh, didn't I indicate that even a write is unsafe? The use of a union there, different members of a union, it's similar. It's not the same thing. The way that you change which member of a union you're using is by assigning to it. It is by assigning to one of the members of a union. So that effectively changes what kind of object lives at the address of that union object. If you have more questions about this, I will be around after the talk in Remo, but I'd like to move on and finish out this discussion of references. Okay, since you can't change what a reference refers to later on, you have to say what it refers to at the time that you create the reference. There's no reference equivalent of a null pointer because you can't change what a reference refers to. A pointer that currently points to null could point to something else in the future, but a reference always refers to the same object. So a reference that started out as null would always be null. That said, the same way that you can get a dangling pointer, you can also create a dangling reference. So same way, you want to be careful about returning a reference to a local variable like this. This f will produce a dangling reference. So given that I can write code that uses references as code that uses pointers, why did C++ see fit to introduce references? It's really for the purposes of operator overloading. References are designed to provide function interfaces that look more like the function interfaces that you could write that we get for built-in types, specifically in the case of overloaded operators. So here I have an enumeration month where values represent different months of the year. I might want to be able to write a loop like this where I step through each month in the year and do something for each month. Now in C, this code just works because in C, enumerations are just integers. C++ doesn't treat enumerations that way. It treats them as user-defined types. So this doesn't compile. The built-in ++ won't accept an operation of enumeration type, but we can overload ++ to make it work for month. Now, if we try and just pass the month by value, it's not going to work because I can write ++m, but the result isn't the value of m changes. The result is we copy the value of m into x, and then we change the value of x and throw away x. Okay, let's try an operator ++ that uses a pointer. Here, it turns out this actually won't compile. The reason it ++ already has a meaning for a pointer to a month. Same way as a pointer to an int can be incremented, you can also increment a pointer to a month. We can't change that meaning by defining an overloaded operator for a pointer. But even if it did compile, it wouldn't work correctly because we want to be able to write this, but that's not what we would have to write. We'd have to pass the address of m into this thing, which is so that we would wind up with something that doesn't really look like a typical ++ operator. So if we want to write our ++ operator that can modify a month object, we really need to pass it in by reference. This version looks right, compiles, does the right thing. And by the way, a ++ operator doesn't actually return void. I've been showing you that just as a simplification, but really it returns a reference to the thing that was incremented. So in conclusion, because you can't use references you can't change what a reference refers to after it's been created. You can't really use a reference to step through the elements of an array or implement a data structure very easily. That's what we use pointers for. Pointers are designed for iteration, for implementing data structures, things like that. References are really in C++ so that overloaded operators can look and feel like built-in operators. References are for writing function interfaces. Okay, that brings me to the end. As I said, I'll be around to answer questions for a little bit in Remo. Otherwise, thank you for coming to this virtual talk. I hope you find it useful. Enjoy the rest of CppCon.